All right, welcome to section 1.5, inverse functions and logarithms. So remember a couple sections ago I told you how important logarithms were. They still are, so that's why we're going to actually cover them again. All right, let's see. So inverse functions and logarithms. The table gives data from an experiment in which a bacteria culture started with 100 bacteria in a limited nutrient medium. The size of the bacteria population was recorded at hourly intervals. So there you go. There's your chart, T hours. There's your population, F of T. The population is a function of time. The number of bacteria, N, is a function of time, like I just said, N equals F of T. Suppose, however, that the biologist changes her point of view and becomes interested in the time required for the population to reach various levels. In other words, she is thinking of T as a function of N. So given the output, what is the input? Right? That's what we're used to thinking of as far as inverse functions go. So the function she's thinking of here is called the inverse function, right? Inverse means do the opposite. Denoted by this notation here, and actually you'll see this is more like the notation here, but we'll cover this quite a bit today. So F inverse, the inverse of the function. In other words, given an output, it will find the input. Thus, T equals F inverse of N is the time required to reach that certain population N. All right, and so there we go. That's the table they made there. So we understand inverses here. Let's compare the functions F and G whose arrow diagrams are shown. Right. So note that F never takes on the same value twice. Any two inputs in A have different outputs, whereas G does take on the same value twice. Both 2 and 3 have the same output 4. Right. In symbols, G of 2 equals G of 3, right? With an input of 3 into the G function, we get an output of 4. Same thing with 2. But f of x1 is not equal to f of x2 whenever x1 is not equal to x2. So any function with that property is what's called a one-to-one function. And when you reach calculus 3 and beyond, you'll work quite a bit with one-to-one functions, so it's good to understand them now. All right, so here's a definition. This is an important definition. Function is called a one-to-one function if it never takes on the same value twice. That is, whenever f of x1 is not equal to f of x2, whenever x1 is not equal to x2. Okay? So let's see, if a horizontal line intersects the graph of f in more than one point, then we see that from figure 2 here, that's this graph here, that there are numbers x1 and x2 such that f of x1 equals f of x2, which violates this definition. Right? So we can see right here with a horizontal line test, right? This is important. With the horizontal line test, if this horizontal line crosses your function anywhere more than once, then your function is not one-to-one. Okay? All right, and this is the way we state it. A horizontal line test, the function is one-to-one if and only if no horizontal line intersects the graph more than once. So remember, if and only if statements, remember they are valid in both directions. Okay, so you could say it the way I just read it. We could also say, if no horizontal line intersects a graph more than once, then the function is one-to-one. So it can be read in either direction and it stays true. Okay, so let's do a couple examples. Let's see. Is the function f of x equals x cubed one-to-one? Let's see, so let's look at that definition here. So I had it all written out for you here. So let's see, if x1 is not equal to x2, then x1 cubed would not be equal to x2 cubed, right? In other words, two different numbers cannot have the same cube. 2 cubed and 3 cubed, definitely not equal, right? All right, so therefore by the definition up above, f of x equals x cubed is one-to-one. And we could prove that graphically here, right? So here's a graph, solve the same problem by graphing. So we'll draw in an x cubed graph. And again, this is one of those graphs you should know off the top of your head. Pretty important. All right. Okay. So this is an x cubed graph. So here's a horizontal line. Only intersects once, right? Doesn't matter where I put this horizontal line. Anywhere on an x cubed graph, I'm never going to hit this graph more than once. So this is 1-to-1 by the horizontal line test. Okay, and remember again, you're in calculus, so one of the things we push in calculus 1 and beyond, especially beyond, you're really not going to have yes or no answers anymore. You need to explain yourself. All right, so if there's any sort of problem like this on the exam or quiz or anything, says, is this graph 1-to-1? What I recommend is, for full credit, you would draw the line in, or horizontal line, and write it out. This graph is 1-to-1 by the horizontal line test. And that's that. That explains it. Okay? All right. Let's see, example 2. So now we're talking about the x squared graph. So remember the x squared graph, that's your basic up parabola with a vertex of 0, 0. All right, so we're going to solve this using the definition of 1-to-1. Well, this one's easy, right? We could say f of 1 equals f of negative 1 when our function is x squared, right? Because 1 squared is 1, negative 1 squared is also positive 1. This all equals 1, but that breaks the definition, doesn't it? We have two different values. Here's x1 and x2. They're different, but f of x1 and f of x2 are equal. So it breaks the definition. All right, so by this, definitely not 1-to-1. Okay, and again, you would show some work like that to prove it. If I ask you to do this graphically, nice and easy, right? We can draw x squared right there. Nice up-facing parabola. Drawing a horizontal line. Just takes one horizontal line here, right? You can clearly see that you hit the graph 2 times. And again, you would write something, this graph is not 1-to-1 because it fails the horizontal line test. All right, so these things are important to do. Make sure you explain yourself. All right. All right, so 1-to-1 functions are important because they are precisely the functions that possess inverse functions according to the following definition. So here's the definition. This one's important to understand. You don't have to repeat it word for word, but you have to understand it. So definition, let f be a 1-to-1 function with domain A and range B. Then its inverse function, f inverse, has domain B and range A. And that's what we're used to when we've, back in algebra, pre-calculus and all that, to find the inverse, don't we magically switch x and y? In other words, we're flipping the input and the output, the domain and the range, okay? And this is defined by f inverse of y equals x. And remember, and I don't know if you know, but this symbol here means if and only if. Again, it's valid in both directions. So f inverse of y equals x. In other words, you input the output to get out the input. If and only if f of x equals y. This definition says that if f maps x into y, then f inverse does the opposite, right? Maps y back into x. If it were not 1-to-1, then f inverse would not be uniquely defined. In other words, we'd have to have multiple, like a piecewise function of some sort. Let's see, the arrow diagram indicates that f inverse reverses the effect of f, right? So note this. This is important to understand. The domain of the inverse equals the range of the function. The range of the inverse equals the domain of the function. Again, we're switching the domain and the range. For example, the inverse function of f of x equals x cubed is f inverse of x equals x to the 1/3, right? Because if y equals x cubed, then f inverse of y equals f inverse of x cubed. So if we plug it in, right? Plugging in the x cubed into the inverse function, x to the 1/3, by our exponent rules right there, we get a 1 exponent, which equals x. And this is the way that you know you have an inverse, that two functions are inverse. Caution, do not don't mistake this -1. In other words, this thing right here, that's not an exponent when it's attached to a function, okay? It does not, this is important, does not mean reciprocal. Okay, so if you see f to the -1 power, I'm using air quotes here, you just can't see me, that's not the -1 power, that's f inverse, okay? If you want the reciprocal of a function, 1 over f of x, and you have to write it like this. Put f of x in parentheses or brackets, whatever, and put a -1 exponent out there. Okay, so let's start working with some of this here. Here's an example. If f of 1 equals 5, so they're giving you this stuff. F of 1 equals 5, f of 3 equals 7, f of 8 equals -10. Okay, so again, in calculus, understanding function notation is extremely important, extremely important. So again, what this means, with an input of 1, an x value of 1, we get an output of 5, a y value of 5. Okay, same thing for the next two parts there. So what they want us to find is f inverse of 7, f inverse of 5, and f inverse of 10. Okay, so in other words, for an output, a y value of 7, what would the input be? Well, you look up here, right? Y value of 7 yields an x value of 3. So there we go. F inverse of 7 equals 3. Okay, so based on that information, we can easily do the rest. For a y value of 5, we would need a x value of 1. And for a y value of, oh, that's supposed to be -10, my mistake there. -10. That x value is 8. Huh? All right, so important that you know that stuff. Let's see, the letter x is traditionally used as the independent variable, the input. So when we concentrate on f inverse rather than on f, we usually reverse the roles of x and y in definition 2. All right, so we talked about this one a minute ago, and that brings us back to how we find the inverse function, right? Remember, we magically switch the x and the y and solve for the new y. We'll do some of those in a little bit. By substituting y for definition 2 and substituting x in for x in 3, so we get these cancellation equations. So these are important. This is how you know if two functions are inverses of each other. You compose them, okay? So in other words, we would have to find that f inverse of f of x equals x. All right, and then we'd have to find that f of f inverse of x equals x as well. Okay, for every x in A and every x in B. That's important. So in other words, you take the function, plug it into its supposed inverse, and if you get a plain old x, then they're inverses of each other, and vice versa. If you take the inverse and plug it into the function, and you get a plain old x, then they're inverses of each other. Okay, so that's what they're explaining there. All right, so let's do a quick example here. Right, oops, we're right here. For example, if f of x equals x cubed, then f inverse of x equals x to the 1/3. So the cancellation equations become, so let's do this. So we're going to do f inverse of f of x, and we're going to see what that equals. So f of x is x cubed. We're going to plug it into the inverse equation. So we're going to do x to the 3rd. We actually already did this one. That's okay. We're just showing the work now. So exponent rules tells us this is x to the 1 power. In other words, a plain old x. We're also going to check it the other direction. We're going to say f of f inverse of x. All right, so we're taking the inverse, which is x to the 1/3, and plugging it into the 3rd power. And again, works out, right? So x, there you go. So by doing this, we just proved that the cube function and the cube root function cancel each other when applied in succession. Now let's see how to compute inverse functions. talked a little bit about this a minute ago, but now we're going to show it. If we have a function y equals f of x and are able to solve this equation for x in terms of y, then according to definition 2, we must have that x equals an f inverse of y. If we want to call the independent variable x, we then interchange x and y and arrive at the equation y equals f inverse of x. So that's that magic trick I was talking about, right? Switch the x and the y, solve for the new y. All right, you've done these before, but we'll do a quick example here. Find the inverse function of f of x equals x cubed plus 2. Of course, what we're going to do, step number 1, always, change f of x to y. Okay. Now again, we're magically, this is not algebraic, this is literally magic. We're switching the x's and the y's, leaving everything else the same. In other words, we're going to say x equals y cubed plus 3. Okay? We switch the x's and the y's. And then we just solve for the new y, right? So we'll subtract 3. Right? Now you got to think, well, how do we get y by itself? Well, if it's y cubed, then we cubed root it. Remember, a cube and a cubed root undo each other. So you can use parentheses, you can use exponents or radicals. It does not matter. Oops. Third root there. And a third root there. So that leaves us with y equals the third root of x minus 3. And there we go. Oh, why did I put a 3 in there? Very odd that I did that. Okay, let's fix that. 2, 2. There we go. Okay. Now, one note, and this is important. Do not leave it as y equals this new equation, because it's not y. This is no longer y. This is the inverse of x equals third root of x minus 2. Okay? That's extremely important. Every single time I teach this class, students mess that up. They'll leave the answer as y equals whatever. I will take a point off for that, because it's no longer y equals. This is y equals up here. This new equation is the inverse. We need proper notation at all times. Okay? Okay. Moving on. Okay, so the next part, this part, you can read over. Just a little bit of information, nothing big there. This is reflections. So the graph of the f inverse is obtained by reflecting the graph of your function about the line y equals x. Okay, just a little bit to remember there. Now, logarithmic functions. So remember, I told you how important these were. We did cover them a previous lecture. We're going to go over them again because that's how important they are. Okay, so I will go over these a little bit quickly because I have talked about them. But again, they're very important. Each one of these log rules is very important. All right, so this first one here, remember, this is the thing I told you was the loop around, as I call it. That is not an official math term. We take the base, raise it to the y, and set it equal to x. So again, this converts from logarithm to exponential and back, right? So remember, this arrow means if and only if, which means the statement is valid in both directions. Okay? Some more rules here. So here, log base b, so we're talking about this guy here, log base b of b to the x equals x for every x in the real numbers. So this symbol means is an element of or is in, and of course that r means the real numbers. Okay, so we should, we will prove that in just a second. Okay, another rule here, this one's good to remember. Well, these are all good to know. That was a bad star. There we go. These are all good to know. So this one here, b, let me clean this up. So what you got to realize here is that's the exponent right there. So this is b to the power of log base b of x. That is equal to x. So it's just a nice way to simplify as long as x is a positive number, non-zero. Okay, so like I said, let's prove that first one in box 7 here. Using the rules of logarithms, prove that log base b of b to the x power equals x. Okay, so let's do that. So the way I like to do this is, well, we know when we have an exponent on the argument, we're allowed to bring it to the front as multiplication, right? In other words, we now have x log base b of b equals x, right? Now, one thing we should know, that right there, log base b of b, so when the base and the argument are equal, the answer is always 1, right? If you're not sure why, let's talk about that. That's important. So log base b of b equals 1. Let's prove that. So this is a side proof. Well, we can use the loop around, right? We definitely know that b to the 1 equals b. So we got it. There's the proof. Okay? So what that means is we have x times 1, which of course equals x, and we got it. Another proof right there. Okay? Important stuff to understand. Not just memorize. Understand. More laws of logarithms. We've talked about these. When you have multiplication in the argument, you can break this up using addition. Same thing with division, but of course in division, the subtraction order matters. Always top minus bottom. And then number 3, we just use that, right? We take the exponent and bring it to the front as multiplication. Okay? Super important. The nice thing about these logarithms, it allows you to do more complicated problems, right, without using a calculator. This is good for your brain, trust me. You're definitely going to want to try this without a calculator. All right, so use the laws of logarithm to evaluate log base 2 of 80 minus log base 2 of 5. All right, so looking at our laws of logarithms above, we have a subtraction here, right, which means division. So we could say this is equal to log base 2 of 80 over 5, right? Okay, so a little bit of math there. 5 goes into 80 16 times. So log base 2 of 16. Okay, so again, we're not going to use a calculator here. We're going to use our brains. We got to do a little manipulating here. This is another thing you got to get good at in calculus. Manipulate it. Sometimes the problem won't do what we want it to do. So we got to make it do it, right? We got to manipulate it. We got to alter it so we can use other rules, other laws to make this work. So what we can do, log base 2, we can rewrite 16. 16 can be rewritten as 2 to the 4th power, right? Now that allows us to use that rule with the exponent. It allows us to take this 4 and bring it to the front. So then we get 4 times log base 2 of 2, and we talked about this. When the base and the argument are the same, the answer is 1. So 4 times 1 equals 4. And there you go. So you took something actually pretty complicated there, and without a calculator, got it down to a single number. Again, this is what we're going to keep doing in calculus. Take things that we take for granted and look at them in different lights. All right. Natural logarithms. Natural logarithms are logarithms. This is a definition. Strangely enough, a lot of students, even at this level, forget this definition. It's extremely important to know this. Memorize it. Not just memorize it, understand it. Okay? Natural log of x means log base e of x. Okay? All right. This allows us to use rules like this. So another important rule right here. It's supposed to be a star. There we go. Natural log of x equals y if and only if e to the y equals x. Now we can look at this and say, well, why is that true? Well, let's use the definition right up above. So I'm going to start here. So I'm going to rewrite natural log of, so here, let me write it out. Natural log of x equals y. But natural log of x means log base e of x, and this equals y. Well, we use the loop around, right? So e to the y equals x. And there we go. All right. Super important stuff. Understand this stuff. All right. More stuff to know. Natural log of e to the x power equals x. Well, let's prove that one. Do I have you prove that one? No, we're going to prove it here. All right, so we're going to prove this statement here. Natural log of e to the x equals x. So here we go. Natural log of e to the x. Well, we know by the rules of logarithms, we can bring this exponent x to the front. So x natural log of e. Now we have to know what natural log of e is equal to. So we are going to prove this separately. All right, so natural log of e. What's that equal to? Most of you probably know, but let's say we forgot. Let's figure it out. Well, let's use the definition of natural log. Definition of natural log is log base e, in this case of e. And we've talked about this when the argument and the base, I said that backwards, but when the base and the argument are equal, the answer is 1. Okay, so there we go. That proves that statement right there. All right, and know this one as well. E to the power of natural log of x equals x as well. All right, so here we go. Here's an example. Find x if natural log of x equals 5. So you're looking at that, I don't know, how do we do this? Well, let's use the information we got. Natural log of x actually means log base e of x equals 5. And when we say find x, that means just get x by itself. Well, we can easily do that here. Loop around. There we go. In other words, convert from logarithmic to exponential. So e to the 5th equals x. And there we go. We isolated x. All right. Fun stuff. Okay. This is another formula you need to know. Change of base formula. So log base b of x equals natural log of x over natural log of b. You can also use logarithms. So you could say log base a of x over log base a of b. As long as those bases are equal to each other, you're good. Okay, and the original reason for this formula here was, of course, way back in the day. Those, even 40, 50 years ago, but especially hundreds of years ago when they were coming up with this stuff, no calculators, right? So they had to do the stuff by hand. So it was way easier to calculate a base 10 by hand because they knew it. They had charts back in the day. So that's why they use this change of base formula. Okay. All right, so here we go. We're going to solve this equation. In other words, we're going to isolate x. So here we go. What do? We got e to the power of 5 minus 3x equals 10. Whenever you see an e as a base, especially with an exponent, natural log becomes your best friend. Right? Remember this? If you natural log, I know this is kind of messy, but natural log both sides of the equation, right? Then we get to use natural log rules. Well, we know 5 minus 3x is an exponent. It's in a logarithm now, so we're allowed to take it to the front. But be careful. We need parentheses here. So it'll be 5 minus 3x, that's that exponent taken to the front, times natural log of e equals natural log of 10. And we've talked about this. This is important. You got to remember this. Natural log of e equals 1. So that's gone. So now this is just plain old algebra here. We know how to do this. So let's see. It doesn't matter how you do it. There's several options. I'm going to add 3x to both sides and subtract natural log of 10. And then, of course, divide everything by 3. So x equals 5 minus natural log of 10 all over 3. And there we go. And if you really want, if you're bored, punch it into a calculator. you should get something like 0.899. Okay? But on a test or quiz, I'm very happy with that answer. Actually, more happy with the answer I pointed to here. Okay. All right, let's see. Next one here. Express natural log of b plus 0.5 natural log of b as a single logarithm. So we're going to use these logarithm rules again. All right, so here we go. Let's see. First, we have a coefficient here, multiplication, right? We can use that rule where this becomes an exponent. So here we go. This is equal to, and always make sure you use equal signs. Equal signs are extremely important. Without equal signs, you will lose points because it's mathematically not valid when you just write out all these different little terms and stuff. You've got to show your equal signs. You've got to show proper work. So natural log of a equals natural log of b to the 0.5 power. Oops, not equals. Plus, there we go. Now that addition allows us to use another logarithm rule where we multiply the argument. So natural log of a times b to the 0.5. Okay, and I would be on a test or quiz, I would be totally happy with that answer right there. But just to be clear, there are other ways to write this answer. So these are just alternate answers. None of them are more correct than the other. You could write natural log of a times b to the 1/2 power. You could also write natural log of a times radical b. Okay, these are all equivalent. All three of these, if you give any of those three as your answer, you get full credit, assuming you showed proper work at the beginning. Okay, example 9 here. Evaluate log base 8 of 5, correct to 6 decimal places. This is for your calculator now. The thing is, most of the newer calculators, you can just literally type this in and it gives you the answer. Let's pretend it was, 20 years ago, and the calculators could only handle base 10 or natural log. So we'll use the change of base formula that we talked about above. All right, so we're going to convert this to natural log of 5 over natural log of 8. Punch that into your calculator, and you should get something like 0.774. I know it says 6 decimal places, but I only wrote down 3. But don't follow my lead here. Make sure you read directions on exams and quizzes. Okay. Let's see. So graph and growth of the natural logarithm. You can see that initially the graphs of y equals rad x and natural log of x grow at comparable rates, but eventually the root function far surpasses the logarithm. So this is on a small scale, right? Looking at the graph close up, this is what happens when you step back a little bit, right? Isn't that what we're supposed to be doing in real life anyway? In any situation, you might see what's right in front of you, but if you step back a bit, you're going to understand the whole story a lot better. And that's what's happening here. These two graphs look very similar, right? On the small scale, but you step back and you see radical x gets a heck of a lot bigger, a heck of a lot faster. All right. Inverse trig functions. These are fun and important. So let's see, when we try to find the inverse trig functions, we have a slight difficulty because the trigonometric functions are not one-to-one, right? So look at this down here. There's a horizontal line. This graph definitely does not pass the horizontal line test, okay? All right, so they don't have inverse function. The difficulty is to overcome by restricting the domain of these functions so they do become one-to-one. All right, you can see from figure 17 here, the one I just pointed at, sine function y equals sine x is not one-to-one. There's your horizontal line. We can see, it's going to cross the graph technically an infinite number of times, right? Okay. But if we restrict sine of x to the domain of negative pi over 2 to pi over 2, then this piece of sine is one-to-one, right? Doesn't matter where I put the horizontal line, only hits the graph once, so it is one-to-one. All right, so this is something you should know. Inverse sine of x. Remember, this is the inverse sine of x. This is not the reciprocal. It is inverse. So inverse sine of x equals y if and only if sine of y equals x. And y is from, so in other words, this is your range. So you do need to know this. The range of inverse sine of x is from negative pi over 2 to pi over 2. Okay? All right, so let's use that information here. All right, so evaluate inverse sine of 1/2. In other words, we need to figure out that that's equal to, I don't know, something. So x, let's call it. All right? Right, actually, we should call it y to be consistent here. There we go. Now I got a question for you. Let's see. So my question is, 1/2. What is that? Not the number. What is it? What does that represent in those parentheses? When you say inverse sine of something, is that something an angle or a value? Right? Well, it's probably easier to think of it this way. Sine of y. Sine of an angle equals a value, right? So let's do that one first. So that's an angle. That's a value. Okay? But inverse means we switch the domain and range, right? So for this part here, inverse sine of 1/2, the 1/2 is the value. And of course the y is the angle. That's extremely, extremely important to know. Okay? All right, so let's do this. This is how we're going to look at these problems. There are other ways to do these problems. If you're asked to do something like this on the exam, you must show proper work. You cannot, repeat, cannot simply say, well, because of the unit circle, this is the answer. That doesn't work. You need to show work, okay? All right, so again, we're trying to find y here. We're trying to find some angle. So what we're going to do is we're going to use this definition up here. Inverse sine of 1/2 equals y means we're trying to find sine of some angle y that equals 1/2. Okay, so this goes back to remembering SOHCAHTOA, right? Sine is opposite over hypotenuse. So first step we need to do here, well, kind of second step, I guess, we need to figure out what quadrant we're working in. Okay? All right, so this part here, sine of y equals 1/2, we're saying sine of y is a positive value. So hopefully you remember the little way to remember where each of our trig functions are positive. It's this, the ASTC. One way to say it is all students take calculus or all students take classes. You probably heard that before. There are other ways to know this. So what we're saying here is all three trig functions are positive in this quadrant. And remember your labeling of quadrants. 1, 2, 3, and 4. Okay. Second quadrant, sine is positive. Third quadrant, tangent is positive. Fourth quadrant, cosine is positive. Okay, all this goes together. And now looking up here, the range of inverse sine is from negative pi over 2 to pi over 2. Okay, in other words, quadrants 1 and 4. Okay, what this means here is quadrant 1 and quadrant 4. That's all important stuff to know. All right, finally, we're going to put all this information together, and we're going to say, or we're going to find out what quadrant this angle y that we're trying to find lives in. Okay, so let's do that. So first, looking at the inverse function, we're doing inverse sine. So that means, and these are just markers, these circles I'm making, where our angle y has to be either in quadrant 1 or quadrant 4, because that's the range of inverse sine. That's what we just talked about right there. Okay. We also know that, again, like I said, sine of y is a positive value. Sine is positive in the first quadrant and the second quadrant. So where's the overlap of the range of inverse sine and the sine of sine? Sine as in positive or negative, right here. Right? So our angle lives in quadrant 1. There's our angle. Okay, so there's angle y right there. Now it says sine of y equals 1/2. SOHCAHTOA, right? Sine is opposite over hypotenuse. So opposite the angle is 1, and our hypotenuse is 2. Now this is where your previous knowledge of certain types of right triangles comes in handy. So down here, side note, right? Just a quick way to remember these. So you've got, let's call this a 30, 60, 90 triangle. Okay. The relationship is 1, 2, radical 3. That's very, very important to remember. Also, another famous right triangle is the 45, 45, 90 triangle. And the relationship of the sides is 1, 1, and rad 2. Okay? These are super important for you to remember. Okay, so using that information, we can see our triangle models the 30, 60, 90 triangle, right? So what we need to realize is, and we could use Pythagorean theorem to find out that this guy right here is radical 3, which means that this is the 60-degree angle. But remember, too, we talked about this before, we're steering away from degrees for angles, and going for radians, right? So 60 degrees is really pi over 3, which makes y pi over 6. So let me clean this up. So equals pi over 6, and finally, after all that work, there's our answer. Okay? Very important that you know how to do this stuff. All right, the next problem here. So we need to find tangent of arcsine of 1/3. Well, if you remember, arcsine really means inverse sine, right? So we're trying to find tangent of inverse sine of 1/3, right? Now we got to analyze again. We got to think about this. Are we trying to find an angle or a value? Well, let's think about this. We said for inverse sine, we're saying this is a value. So inverse sine of a value gives us an angle. So inverse sine of 1/3 is an angle. And when we take tangent of an angle, we get a value. Okay, so in the end, we're looking for a value here. Okay, very important to understand this stuff. All right, so we're going to work our way from the inside out. We're going to start with inverse sine of 1/3 equals x. What that means is we need to find the value of, this is an angle. Now we're trying to find an angle. We're trying to find the angle. Oh, no, see, this is where I'm getting everything messed up. So this is something different. So let's call this guy y. There we go. This makes more sense. So we're trying to find sine of the angle y that is equal to 1/3. So we have inverse sine. We know the range is quadrants 1 and 4. Sine is positive again. So here we go. Let's figure out the quadrant we live in. So inverse sine, the range is quadrants 1 and 4. Because sine is positive, right? Positive 1/3. That's quadrants 1 and 2, where sine is positive. So the overlap is here. So our triangle lives in quadrant 1. Again, don't assume that's always going to be the case. All right. So what we got to do next is, okay, so here, let's see, we got y. This is angle y right here. Again, sine is opposite over hypotenuse, so this is 1 with a hypotenuse of 3. Now be careful. Again, you'd be doing this without a calculator. Of course, if we were in the physical in-class situation, which we are not this semester. But it's good to know how to do these by hand without a calculator. So we would have to say, well, you know what, the problem here is this does not match a 30, 60, 90 or a 45, 45, 90 triangle. This is something different. Okay, so what we would have to do is use Pythagorean theorem to find this third side down here, this base side, which if you use Pythagorean theorem correctly, you should get radical 8. Now, you're thinking to yourself, well, without a calculator, how would we figure out this angle if it's not 30, 60, or 45? Well, then you have to ask yourself, wait a minute, do we need that actual angle? The answer is no, right? Because look what we're trying to find here. We're trying to find tangent of this angle. Tangent is, so think of SOHCAHTOA, tangent is opposite over adjacent from our angle y. So right now we're at tangent of y equals x, right? But again, tangent is opposite over adjacent. So 1 over radical 8. And there we go. Now, of course, you've been told, throughout your mathematical careers, don't leave a radical in the denominator. So we would do what's called rationalizing the denominator. So again, this is called rationalizing the denominator. Hopefully you're familiar with it, but we would multiply top and bottom by the denominator to get rid of that radical, which would be rad 8 over 8. Okay? And there we go. There's our answer. That's what we've been looking for. Okay. Make sure you study those. So we talked about the range for inverse sine. There it is. I'm just going to kind of skip down a little bit. So this one's important too. The range of cosine is from 0 to pi. In other words, the range of inverse cosine is quadrant 1 and quadrant 2. Okay. And down here, we're going to go down here. Inverse tangent. The range is from negative pi over 2 to pi over 2, which in other words, the range is quadrant 1 and quadrant 4. Okay, so you need to know the ranges. I'm going to write this. So this stuff down here, not necessarily, I'm not going to write all that. You don't need to memorize this. No memorize. Oh my gosh. Okay, you don't have to. You can if you want. I would never tell you not to learn something. But let's talk about these ranges again of inverse sine, inverse cosine, and inverse tangent. So here's a great graphical way to remember this. So ranges of inverse trig functions. Okay. The way to remember it is across the top is inverse cosine of x. That's the range. So in other words, quadrants 1 and 2. Yeah, quadrants 1 and 2. And across the right here, top to bottom, for inverse sine and inverse tangent of x. Okay, so again, that's the easier way to memorize the ranges. Okay. All right, and that is our lecture. Thank you very much.